Hey MXNeters, so that's the second part of our talk. We're going to talk about performance tips and tricks. So in the first part, to summarize, we've seen how we can visualize the performance of the hardware by measuring the GPU utilization, the memory, I/O, and the CPU utilization and how much RAM is being used. We saw how we can also monitor the training of our model, and now we're going to see how we can actually tweak the code to get these metrics up. So first slide I want to show you is a summary of what we're going to talk about. We're going to see first how we can go from a naive implementation and do a set of optimization that are going to be additive. And we're going to show that we can get up to 5x improvement by just doing a few small tricks that in the code are very minimal changes, but that can really dramatically improve the performance. The first one we're going to talk about is to make sure we don't have an I/O bottleneck by using multiple workers for the data prefetching. The next step we can do to get more of our GPU utilization is to hybridize a network that will let us use the symbolic execution engine. The next step we do is to increase the batch size so that we use more of the parallel cores of the GPU. Then we're going to tweak the synchronization call to minimize the time the GPU is idle, waiting for data to be copied from the GPU to the CPU. And finally, the last optimization we do is to use float 16 mixed precision instead of float 32. So let me show you in details how that works. This notebook is available in a repo that I've put in the description of the video, so you can check it out and run it yourself and see for yourself the impact of the different optimization that we're going to do. So I first import the network, import MXNet, and then I have a few more utilities that are usual if you're familiar with Gluon. Set a few seeds for reproducibility, and now we're going to skip the part that you've seen already. About visualizing the network, and then we're going to move to the performance tricks. So here the first thing we do is to load the model in memory. So we're going to get a untrained version of ResNet 50 from the model zoo. That's this line here. So we're going to basically load the network structure into memory, but the weights are going to be randomly initialized using the Xavier initialization. So we do that, and then, for example, if we check Grafana and we check the last 5 minutes, we should see that here we had just some activity where the network was loaded onto the memory, and then we can go on. So for the data bit, we resize the Cipher10 dataset up to 224 by 224, which is what is expected from ResNet 50. And we create this dataset that we pass to the data loader. Data loader is a class that's going to take care of splitting our dataset into batches, and we're going to use that for our training. The loss, we just use the softmax cross entropy loss, and for the metric, we use the accuracy. Our optimization algorithm is going to be a stochastic gradient descent with momentum and weight decay as specified here. And let's look at the naive attempt. So if you're familiar with Gluon, that's a typical training loop. We loop through a certain number of epochs. In that case, we early stop after 200 iterations. So we're not actually going to go through multiple epochs. Then we get the data from our data loader on this line. And then we put the data onto the GPU. Under the autograd scope, we are recording the operation that are happening on the forward pass when we pass the data to the network. We compute the loss from the output of our network versus the labels it should have predicted. And then we're going to compute the gradient of the parameters of the network with respect to that loss. So we do loss.backward. Once we have the gradients, we can now update our trainer. We can update our network according to a specific optimization algorithm by calling trainer.step. It's going to update every parameter according to the gradient we just calculated, and so on and so forth. Here we just have a bunch of metric that we are printing and we're passing to TensorBoard. So TensorBoard right now is empty, but as soon as we're going to start running this, we're going to get the accuracy being printed as the number of samples per second. Okay, so let's run this. So the data is loaded. You can see the accuracy starts at 0 because the model is not trained. And we see we are around 150 samples per second. And the accuracy goes up. And if we check Grafana, we should see here that we have indeed some activity happening, but we see this very bumpy profile. And this shows that the GPU is actually waiting for data before it can process it. So you can see the utilization going up and down, up and down, up and down. What we would want is to have a constantly high utilization. If we look at TensorBoard, we get our data is coming through. We see accuracy going up and the number of samples per second kind of staying around 150. So if we look at the CPU utilization now in HTOP, we can see that there is indeed only 3 cores being used. So that's where our bottleneck comes from. We need our data to be loaded in advance ahead of time so that the GPU is ready to consume it. So to do that, we do a very simple trick. It's literally one little change of code where we say instead of using the main thread to do the data loading, we're going to use asynchronous workers. I can prepare batches in advance so that when the GPU needs it, we can just copy it straight to the GPU. So we change the data loader to use the same one, except we use multiple workers, reinitialize the network, and we run the exact same training loop. So now we can check. If you remember, we had 150 samples per second, and now we are up to 318. So clearly, the bottleneck is not the CPU anymore. You can see that most cores are being used, but none of them are reaching 100%. And if we look at Grafana, utilization is a lot smoother than previously. So just with using multiple workers, we're almost at a 2x improvement. Actually, we had above a 2x improvement, 200% faster. And if we look at at this number of samples per second and the accuracy, we reach the same accuracy. Oh, it's very similar. Actually, it's a little bit better, but it's just due to stochastic effect of the training. And here we can see if we move from rather than comparing step by step, iteration per iteration, we look at actually the time. We can see almost more than twice faster. We reach a very similar accuracy. So now, how can we improve again on that? So if you remember what I said about Gluon, it's using a imperative API, but we can hybridize this network. And we can run the hybridized version, which is the symbolic version on the MXNet engine. So this again should show some improvement versus the previous method. And if you remember, we were around 315. Now we are around 330. Depending on your network, hybridizing can give you up to 2x improvement. Here, we don't get that much of an improvement because we also already doing a pretty good job at utilizing our GPU. So we go from 9092 to a little bit better at 94. But if you were in a situation where your GPU wasn't being utilized a lot because maybe your network is quite small or for other reasons, then hybridization would give you a very big performance boost. Okay, so now we were working on a fixed batch size of 48. If we look at Grafana and we look at the memory utilization, we can see that we have actually some spare memory. So one thing you can do is use bigger batch sizes. So we're going to move to a 96, so double the batch size. Everything else stays the same. So again, we need to recreate our data loader with this new batch size, reinitialize our network, and let's run the training loop. So if we look at the Grafana utilization, we see again we have very high utilization, even slightly higher. Here we're 93, 94. Here we're going to reach 97, 98. So our GPU is really fully utilized, and that's really what you want when you're doing um, deep neural network training. And again, we're not sacrificing any accuracy for that. We have very good accuracy, and our speed is getting even higher. So one simple thing I haven't mentioned here is when you increase your batch size, you're going to pass twice as many samples in each batch. So one kind of rule of thumb is you need to adapt your learning rate. For each batch, your gradient is averaged among your entire batch. So you have twice more samples. The idea is you get twice more confident about the update the gradient is giving you, so it's fair to double the learning rate. If you go in very big batch sizes, some recommendation, for example, from the Facebook paper, is to actually first do a warm-up where your learning rate is not that high, and then you can linearly scale your learning rate with a batch size. So in that case, I just doubled because we're not trying to reach a given accuracy. We're just trying to improve the throughput while maintaining a similar accuracy. So that was for the fourth improvement, and you see that we're reaching around 350 samples per second, up from 330 samples per second. And we started with only 150 samples per second. The next one is slightly more complicated to explain. So you need to understand that MXNet Gluon is using eager execution, which means every operation you are executing or telling Python to execute are going to be enqueued in the backend engine. And they're going to be executed when all their parent dependency are met. So I'll go a bit more in details when I go back to the slide to explain exactly what's happening. But really the idea is you don't want to do a synchronous call. For example, when you update your accuracy, which is when you need to copy your label to the CPU to compute your metric, you don't want to do that and then call these lines, because these lines copy the memory to the GPU, and then the GPU only can start the work. What you want to do is you want to call this line first, say, hey, copy the memory to the GPU whenever you're ready, and then you say, compute the metrics. So what's going to happen is in parallel, it's going to copy data from the CPU to the GPU, copy the old output from the GPU to the CPU, and when it's finished computing the metric, the next thing it's going to do is going to be to compute the next pass. But it doesn't need to wait for the memory to be copied to the GPU before it does that. And that can give from small improvement to very big improvement when we have gigantic batch sizes that needs actually takes quite a bit of time to copy from CPU to GPU. And you also see a big improvement when you use small networks, because the smaller the network, the faster but the less time you're going to spend on the actual computation and the more time you're going to spend on the communication overhead. And this really helps with the communication overhead. So let's reinitialize the model on a different GPU. In this time, we try the second GPU. And let's run that and let's see what we get. So if you look at Grafana, we are again getting very good GPU utilization. 90, 96, 97, very close to 100%. And if we look at here, we go from 350 samples per second to 360 samples per second. So decent improvement here. But like I said, it depends on your cases. Here, because we've optimized already quite a bit, there is not much room left for improvements. But we still see an improvement. The last one, and maybe one of the most effective optimization we can do, is to use half precision. Instead of float 32, we use float 16. And the important bit is this one. We're going to cast the net to be float 16. And what we're going to see is, because the weights are represented only as half number of bits than float 32, they're going to be computed faster, the multiplication and addition and everything, and they're going to use less memory. So potentially you're going to get a improvement from the simpler multiplications And also, you could potentially even double again the batch size because space-wise, you would have the space to store to use twice as much memory, and because it's the float 16 rather than float 32. So you kind of get this double boost, but in that case, we're going to just stick to the same batch size just to see what the solely the float 16 change would give as an improvement to your network. So reinitialize the net, cast it as float 16. Everything stays the same, so that's the only line that changes, and then we run the training. So if you notice, since the since the batch size change, I'm only running 100 iterations because each iteration has twice as many samples as in the beginnings. And if you look here, we see massive improvement. We go from 360 to almost twice as much, twice the speed to like around 730 on average. So extremely good performance. And we can see here effectively we get very good utilization, north of 90%, and it's super fast to run through all these samples. The question is like, do we get good accuracy? Well, the answer is yes, we get very similar accuracy. So here we see the final accuracy is 0.20, so might not have been reported here because maybe the flushing of the buffer is not as good, but we basically reach. Okay, let me try to force a flush. Yes. Yeah. So we reach very similar accuracies than the other ones, like around 0.20, but in basically 5 times faster than the original implementation. And if you're familiar with Gluon, really, the original implementation is what you will see in most places. So it's very important to look at the code, really optimize, look at your metrics, look at your CPU, look at your GPU. Because rather than upgrading from one GPU to 8 GPUs, maybe you can get a 5x improvement just tweaking your code and making sure you're utilizing 100% of your hardware. So one good data point is to put some memory, uh, put some data onto the GPU, and then run a few passes through your network. And that way you can really see the the theoretical speed that your network can achieve if there were no I/O overhead. So if we run it here, we see we are around 800 samples per second, and here we get 750, 730. So it's not too bad. We are really close to the maximum sample speed if we had no I/O overhead, which means we really did a fairly good job at optimizing our I/O pipeline. Okay, so if I go back to the slides, to summarize the optimization, so one I haven't mentioned in the notebook in the environment. So MXNet comes in a variety of flavors. For example, if you're going to do CPU inference, you can use, if you use MXNet MKL with the MKL DNN Intel library optimization, then you're probably going to get up to 32x speed increase if you had, for example, 32 CPUs. So it's really massive. But even for GPU, if you use MXNet-CU92 versus CU90, which is the CUDA version, you can get you can take advantage of the speed improvement that came with the later version of CUDA. So first thing, make sure that you're using the fastest version of MXNet that's available to you. Then make sure you're not I/O bound. And to detect that, look at your GPU. If you see less than 100% utilization or like very low in the 20, 30%, it's probably that you're I/O bound. Check your CPU. If you have a low CPU, it means you're not utilizing enough workers, or you can use more workers. Let's say some of your cores are like maxed out and the others are doing nothing. So simple optimization, use the num workers argument of the data loader, and that would help you a bunch already. And if you're already doing that and you see like every CPU being maxed out on your data loading, then that means you probably should be doing some offline pre-processing. So let's say you're resizing your images, then resize them on a one-off and store a version of them resized very close to what you need so that you can alleviate the load on your CPU. And then you should see your GPU going up because it's not waiting for the data to be prepared just yet. Next improvement, once you're ready, like you've debugged your network, you're happy with it, it's running exactly like you want, you just want it a little bit faster, then use hybridize. So I'm not going to go in details. Not every network can be hybridized in Gluon, but most of them are if you're using all the traditional kind of building blocks. And if you're creating your own block, it's very easy to make it hybridizable. And you can refer to the tutorials that you have on the MXNet.io website. Fourth improvement, look at your upper parameters. Very often you'll see that, say you use a NVIDIA V100, you have 16 gig of RAM available. Maybe you're not using all your memory that you could be using on this GPU. So increasing your batch size will make sure that more operations are done in parallel on your GPU, and that can give you another boost. So you don't want to, if you go back to the smart synchronization calls, I don't know if that was very clear, so I'm going to show you an example of what happens. You don't want your GPU to be waiting for the data to be copied onto the GPU. So that's really efficient for small networks because that's the communication overhead becomes bigger. So let's look at the traditional loop. You say, move my data to the GPU, I do my forward, I do my backward, I do my update. I get my metric, I compute my metric, and then the metric is a synchronous call because it's happening on CPU. So the MXNet engine is waiting for the prediction to be ready, send them back to the CPU, it's computed, and then you move to the next iteration of the loop. Copy to GPU, forward, backward, metric computation, so on and so forth. So by doing the smart synchronization code, and if you look at the code, what I'm doing is I'm just doing the metric calculation of the previous loop after the data is copied to GPU. It's happening like that. So the first pass, you copy to GPU, you do your forward backward, then you call copy to GPU of the next iteration. The metric computation is being done, but in parallel, the data is copied to GPU. So when you're ready with when the metric computation is finished, you can straight away go to your forward backward pass, and so on and so forth. So that way you can save a bit of time and make your entire network a lot more optimal. Final tweak that we've done, we moved from float 32 to float 16. That was, and again, a massive performance boost. We got almost twice faster than the previous training. And it's really as simple as doing net.cast float 16. So and we didn't see like a big loss of accuracy. So try it with your use case, see if that works for you, but that could be a very good way to make your training a lot faster. In terms of performance here, we only talked about the throughput, samples per second, but really what you want is time to accuracy. How long does it take you to reach a given accuracy? And here you can tweak other parameters, and namely the optimizers. So we fixed the SGD with momentum, but you could look at a grad, at a delta RMS prop, different type of optimizer that might give you sometimes lower samples per second throughput, but if the optimization is going faster, then you would get a faster final accuracy. One last thing you can do if you want to measure your performance and really understand what's going on is a profiler. And I'll show you a quick example of how you can profile code in MXNet. To do that, you can import the profiler from the MXNet module. You get the profiler package, set the configuration where you want the output to be, and then you just run a little like training. The two triggers of the profiler is state run and stop. So you run them like this. You get your output, and then you do profiler.dump. This creates a JSON files that you can then put into the tracing. Um, tracing tool of Chrome, for example, you just load it like this, and then you see all the different operations that have been done on your network. You can um, look at specific slices, really see what's costing, what are the costly operation on your network, and so on and so forth. So that's really useful because sometimes you don't really know if the fully connected, for example here, uh, is more expensive than the convolution. And here we see that the convolution total cost is like 3,000 millisecond. And here we see that the fully connected is a fraction of that. So because when you create a network, you don't always know if you say like an LSTM with 100 hidden units or 300 or 500, you don't always know what's going to be the impact on your training performance, so you just try things. Profiling really lets you compare and size them according to what they do to your total like training time. So it's really interesting to really understand where the time is spent during training. And for example, in this example, you can see that the pooling and activation operations are relatively small compared to the convolution of the fully connected one, and so on and so forth. So very interesting to look at. So to conclude this two-part talk, I would say very important, use first Gluon to debug and iterate quickly. It's very easy to change your code, and hybridize, optimize for speed. So that's using all the tricks I mentioned earlier. Next is really know your model. So during all these operations, make sure that you have set up the right metrics, the right tools to visualize your network architecture, to visualize the performance of your GPU, of your CPUs. Really get familiar with what's happening in the environment and inside the training itself by tracking the loss, the accuracy, the samples per second. And yeah, so that's it. Thank you very much. If you have any question, please follow up on GitHub or my email address and reach out to me directly, and I'll be happy to answer any question, or you can leave comments on the YouTube videos.